So Roi, CTO at Panoply. Panoply is basically an end-to-end data management platform for analytics. It's cloud-based. You can think of it as like your automated data engineer or data scientist that does all of the cleanup work and all of the maintenance and DBA work and leaves you to focus on what's important, on the real analysis, on the deep queries, on the business questions. And at Panoply, we use a stack of technologies ranging from Redshift and Hadoop to S3 and CockroachDB, among others, Elasticsearch, for example. And specifically, I wanted to talk about CockroachDB because it's a pretty awesome database. It's kind of new, and I think it signals a little bit where the future of databases is going. So we use CockroachDB internally for all of the like users management, metadata that we keep, all of the encrypted data, the data sources, basically all of the management layer on top of the data itself. And we started out with Mongo and moved over to Cockroach, and I think we've learned some interesting things about it. So in this talk, I'll talk a little bit about, it's going to be really short, unfortunately, but we can follow up later. We'll talk a little bit about what Cockroach is. It basically based on the Google Spanner paper, if anyone is familiar with it. It has NewSQL. It speaks NewSQL, which is this kind of new variant to SQL, or new approach to SQL maybe. It's scalable, extremely survivable. I guess this is why they picked the name, CockroachDB. Like it's supposed to outlive all of us. Like be the last remaining artifact of humanity when we're all gone. And finally, it's very strongly consistent, and I think this specific property is what makes it unique. So what Google Spanner is all about? The problem that Google was set out to solve was that they had their advertisement database, like all of the ads they run across the globe, and they had at each data center in different continents, they had tens of thousands of servers. And each one of these servers were replicating across continents, right? So it was massively scalable, high latency, wide area network kind of system where you can imagine how many failures they have every day in something like that. So they need to come up with something new, but specifically the main property they needed was consistency. So unlike all of the new fancy big data ideas, they couldn't compromise on eventual consistency or something like that. Like if someone made a bid for a keyword or whatever, it has to take effect immediately at that microsecond, and it can't propagate later and take some time, some latency time. So we're going to go back to that point towards the end of this slide, but specifically the language that they picked is SQL, and I think there's an interesting history lesson here. Basically, SQL started out back in the 70s-ish, maybe even before that, and it grew over the decades into this very powerful, expressive language, right? It has evolved to support a wide range of use cases, and that made SQL very, very powerful, but also limiting. It's really portable, it's transactional, which we know, and purely relational. And what made it, the problem with it, I think, is that it's difficult to implement. So if you set out to build a new database now, and you need to support SQL, that's intimidating thought to even get started with. So, the NewSQL guys came up with this trick. They call it NewSQL. We'll just forget about the whole thing. And we'll just build our own API. And it's great, it's simple, it's quick. We've seen great databases built this way. But I think, looking back, it didn't always mature that well. Because Eventually, the use cases didn't change. The expressiveness that we as developers need is the same. The requirements that we have are the same. And we didn't have the language to support that. So that's why Mongo now have SQL layers and Hadoop as SQL. Eventually, you either have to develop the same level of complexity anyway, or you need to come up with some SQL layer. And most importantly, I think the notion of NoSQL coupled two different ideas. One is the language the language you speak with the database. The other is the relational nature of the database. And these are two completely separate subjects. It means that basically you can use SQL to query anything. It doesn't have to be tables. It doesn't have to be with a strict schema. It can be anything you want. You can query JSONs in Postgres with SQL. It works. But we got used to the idea that NoSQL means non-relational, and they have to come together. And this is the concept of NewSQL, which I love, I think. It goes back a little bit. It's kind of new, a new term. Some new databases are starting to pick it up. And it basically says, okay, we still want to use the expressiveness, the semantics of SQL, but not necessarily follow the same strict, purely relational model. And that's what they are doing. So the language is going to change a little bit. It's not going to be a standard SQL, like it's not MySQL or Postgres, exactly. It's close enough, and the spec is evolving also. So I think that's interesting to see how we did this whole road trip and ended up pretty much where we were in the beginning. How it's built, just quickly, basically, CockroachDB is a monolithic distributed KV store, where basically, everything, it's showing you tables, again, SQL-ish, it's pseudo-relational. So you get to see tables, you get to see schemas, but underneath the hood, the way that it's actually stored is using RocksDB, which is this key value store. So basically, every cell in your data becomes a value to a key. So if you have a row of 10 columns, you'll get 10 different keys. And obviously the key name, and the key name is prefixed by the table name and primary key, etc., such that you have the way to get some data locality here. So you can figure out how to build the columns, how to build the rows, the tables, the primary keys, in order to make, efficient, to model your data efficiently, to be local where you want, to run joins or whatever. And then each batch of these key values is basically a key range. It's stored in its own node. And these guys, it's a bit of a simplification, obviously, but these guys get replicated across data centers, hopefully. So we get these chunks of key ranges that get duplicated and replicated all around. And that's pretty much how it looks like. The replication and everything, this is pretty standard. It's using two-phase locking, two-phase commit to basically take any one of these nodes. On write, it's locking on write until it reaches consensus. And that's what makes it, this is maybe part of the trade-off they have to give for this consistency. It means that they have to achieve consensus on every write. They can't let it propagate later because it's impossible to have a single instant of inconsistency. And of course, in case of node failure node failure is an easy case. They just reach consensus with the other nodes to figure out, what should be the return value when you try to read a value back. But more complex than that is when we have network partitioning, where we have two parts of the network being unable to communicate with each other, but each one is still available externally. And that creates the illusion that each one of these guys is its own cluster, right? And each one can continue getting writes and reads separately and evolve separately. And again, the way that it's solved in Cockroach and Spanner is the same idea of always doing consensus. So that's a cost. That means that, for example, you can't have this case where you have tens of servers running and you communicate with them and eventually they will converge into the same state. Instead, a big part of your network in that case won't participate, will just reject all of your queries.
Quick question, why did your last slide have RocksDB on it?
What?
Your last slide, your previous slide?
The previous slide has
Yeah.
RocksDB. So RocksDB is the internal, it's like LevelDB, it's like the internal storage engine that they use within Cockroach. It's just a key value store, distributed key value store. And they basically build the whole, it's open source, by the way. I think it goes without saying. So they just build the whole SQL layer and schemas and tables representation on top of RocksDB. Forward. Okay, so strong consistency. I think this is a controversial one because, I think at least I've gotten used to the idea that chasing strong consistency might be a bad idea because you always have to synchronize and it's really difficult. And why do we need it? And you know what? For analytics, for example, I think that makes a good case. Maybe you don't need strong consistency. But when you deal with sensitive user details, when you deal with changes that should take effect immediately. So from one of the videos that I saw preparing for this talk, he said, consider that you build a social network and some user uses your social network and he wants to post a really, nasty comment about something. But before he does that, he removes one of his friends because he doesn't want him to see it. Imagine what would happen if we wouldn't have strong consistency. There is a chance that he would remove the friend, write the post, and still it's eventually consistent. There might be a few seconds, in some cases, that it won't update. And in that case, we should probably just sleep for a few minutes to solve it. It really doesn't make sense. So in some cases, we can't really predict how users are going to use our platforms, and we need to think about that. But I think, I believe that when we touch sensitive user details, user information, we want to be really strict about it because we don't know what kind of edge cases users will get to. So how they achieved it, there are two steps to it. First, there's multi-version lock-free reads. That's pretty standard. What it means is, this is what you see here on the right, that when I said before that it's like a simple key value, I kind of lied, because each value has multiple timestamps, so multiple copies. And each time you write to a key, you create a new copy. And basically, what we want to do is assign a timestamp to each one of these keys. So every time we write to the database, we write a value for the key, and we also attach a timestamp to it, of when it was written. And what happens is, for example, here you can see that we are writing a new value for this key at timestamp 2, but reads are still taking place with timestamp 1. And that means that I can write everything we want here, and until we increment this read timestamp, that won't be visible. That gives us the ability to kind of take snapshots of the database and say, hey, I want to look at how the database looked at timestamp 2, 3, 4, etc. And that's why it's also lock-free reads, because we don't care about it. We don't care about what kind of writes are happening in the background. We don't need to lock anything for it. And that's great. The only problem, and I think this is the interesting part of what they did with Spanner and Cockroach, is how do we get that number? So, again, we have a distributed system across many data centers, across continents, hopefully, and we have two queries happening almost the same millisecond. How can we guarantee? How can we determine which one was really before the other? And if we get it wrong, we might get the post before the removing of the user. So we have to get it right. So Google came up with the idea that they call global clock. It's pretty cool. So what they did is, I'll first describe the API. I think that's the useful stuff, but maybe not the cool stuff. The API works like this. They basically created a clock server that they can query to get the time. Except that the time, this is a call to time.now. This server doesn't return the actual time. It returns a range. It takes into account the uncertainty in the clock. So it gives you a time and some epsilon, which is the uncertainty, like how many microseconds or milliseconds we might be off. And with that, you get the earliest time and the latest time. So you basically get 2 time stamps when you ask for now. One of them is the earliest possible across all of the servers in your cluster that you would ever be able to get if you would call now on that server. And the other is the latest. That's pretty much it. And they do something kind of funny, is that they may finish processing the query at a certain point, but they will wait out the uncertainty. So they will actually sleep until the time. It's basically they commit in the future and they wait for the clock to run out before they tell the client, hey, you successfully removed that user from your friends list, or you successfully, posted that post. And of course, the idea is that while this commit wait is taking place, it's just asleep, so other threads can run, but it's basically slowing down the whole system just to get this consistency. So that's something to think about. And the biggest difference, I think, between how Google Spanner does it, and Cockroach, is that Google created a cool new hardware for it. They're using GPS clocks and atomic clocks attached to some server that you can communicate with to get an API, and normal NTP servers. So they just collect all of the time from everyone, periodically, from all of these servers, in order to compute the uncertainty. Kind of difficult to do it for us until at least it's open on some platform. So in the meantime, though, we can pretty much reach the same level of the same algorithm, the same idea of what they do now, just with NTP, except that the epsilons will be bigger. So we will be spending more time. We'll have more uncertainty in the clock, but we would still be able to achieve the same level of strong consistency. So I wanted to show you a demo, but I don't have time for that. But it's pretty simple. It's pretty much a JDBC database. You spin it up on Docker, hopefully, and play around with it. Pretty cool. It is still in beta, but they took an interesting approach. Most of the code is stable and production ready, from my point of view. But there are some features that are just not yet implemented. So for example, some of them are joins. That's a big one. Distributed SQL. So the query processing actually takes place always on the node that you reached for that query. It's not like massively parallel, like Redshift or something like that. But for transactional databases, might be fine. So they are working on some Swarm and Mesos deployment. And the Evergreen database, that's a cool little discussion that they were having. I don't think they're going to do it. It's too insane. But the idea was that you install this database, and it will update, kind of like how Docker for Mac updates itself. So you'll get something like that. Security and critical fixes will just get pushed to you without ever having to do anything. And again, looking at the future of databases, I think this is something that I learned from this whole experience with moving away from Mongo to something like that. Is that I really believe in the concept of SQL as a language, not necessarily as, a purely relational database model. Operational scalability, I think that's something that's so, we don't talk about enough, which is not we're used to talk about scale, in my opinion, in terms of how much data we have, or how much queries we run, and that's fine, that's the technical aspects of it. But I think at some point, especially for us when we started with Mongo, you get to the point where you have the operational stuff gets too big and complicated for you to keep up with. Like the number of people coming up with different use cases and different questions and different types of queries. We needed something robust. We needed something that I can tell anyone, hey, you can, here's the replication, you can take your workbench and just, do whatever you want. So give me the ability to, or use some off-the-shelf tool that's really easy to use, or use Tableau or anything like that. And I think getting that, the ability of the company, the organization to scale is also important, not just the data size. Greater semantics at scale, I think this is something that we've all learned that, the idea of this gimmicky, nice little databases that just support a single function, it's cool, but and it's great in many cases, but I think it just hides sometimes the complexity. You will have to pay it somewhere. If your use case doesn't change, you would need some place to have that kind of more complicated semantics, more complicated query language. And finally, I think is the lesson that I learned that, and I see it a lot around me, of moving back to the less exotic, less crazy databases. I see a lot of companies nowadays moving back to Postgres, which I think is great. I don't have anything against NoSQL and all of the new ones, but I think we might have overhyped them sometimes. That's my point. That's it. Yeah.
So you mentioned that you used Mongo first, and then you moved to this.
Right.
Can you tell us a little bit about your use case and why you decided to choose this as opposed to SQL?
Yeah. So I think that's a good question. I think so. Okay, I can touch first on why not Mongo, which for us was we needed more semantics, more structure. More stability. And, I think also from my experience, when I want to really scale it up, it can be difficult at times, although, people have made great things with Mongo. But specifically why this, I think when we were set out to, so we realized, we want to rethink the database that we use to store all of our user details. We did some research and we were looking for something really strict and stable. And yeah, the choices were this or Postgres. I think I like the idea of this new way of thinking about strong consistency and how it can be achieved in a way that's not achievable, not even in Postgres, for example. There you can get serializability, you can get the same level of external consistency. So that's pretty much it. I have to say, for me, between these two databases, it was mostly just a choice of, we like the idea and we wanted to try it out. And so far, we've been really happy with it.
So it wasn't any kind of killer thing you couldn't do
No,
with Postgres?
not killer feature, no.
No scale issues?
Yes,
Scalability? What do you mean? Scalability here is, I don't know if I showed you this, but this guy, they claim they were able to run it at 4 exabytes, 4,000 petabytes. It's a scale I can't even imagine. What?
Is that something you needed?
I don't need it right now, but definitely if there's, I learned, my lesson from the previous company I worked at is that I would rather, plan ahead and choose the technologies that will make it easy for me to scale instead of making hasty decisions sometimes and just take something like Mongo, which is really easy to start using, and then I might regret it later on, which is what happened to me in the past. So I really wanted to research that and choose a database that will be able to scale with. Not 4 exabytes, but the question of scalability is absolutely solved. Like, I'm not at all worried with scalability here. It has been tested in petabytes of data and got great results. So, any other question?
Maybe I missed this, but how long has Cockroach been around, and who are the major contributors? Google?
Yeah. So Cockroach was started by, I think, 2 or 3 guys who worked on Google's panel and left to start CockroachDB. They are ex-Googlers that worked on it. It has been in development, I think, 2 years. Spanner, which is what it's based on, is in production for 4 years now, running all of the databases, all of the advertisement database at Google. It's written in Go.
And how do they, is there a leader node, or is a quorum in terms
No, it's all, there is a quorum. Everything is with a Raft consensus. Everything is, there's no leader. You can hit any of the nodes to send the query. Yeah, there's no single point of failure. The whole idea is anything here can fail.
In terms of doing backups, any challenges there, or you don't need backups?
To back it up? Yeah, because it's replicated, we didn't go for an additional backup, although it's probably wrong. You probably want to do backups anyways. Yeah, just in case. But
yeah, for logical corruption. Yep.
What?
You want to do a backup for logical corruption, I assume, right?
Yeah, exactly. Exactly. For logical, for human errors, not for yeah.
And does it support ANSI SQL? Does it support ANSI SQL or?
Yeah, it supports my SQL variant of SQL. I think it's pretty. Actually, it's kind of the one thing I hate about it. I don't know who made that mistake, but they are using the Postgres protocol with the MySQL language. So, you might use a workbench or something for Postgres, and it will, write queries in Postgres, which wouldn't run on. But I don't know. They're working on changing that.
That's fine.
Yeah, but yeah, it's pretty compatible and with ANSI SQL for the most part.
Are there other things you miss about it? Miss about having a more traditional database? You mentioned that joins is on the roadmap.
Yeah, so joins is absolutely one of them. We currently avoid that more on the application layer, by just making the join there. But yeah, I think the distributed queries, but that's just a performance issue, which hasn't been really a problem. So no, we didn't run into any real problems yet. But we're early on, and we will update how it goes. Okay, that's it.